Okay, so in our previous session we have seen that what is the difference between analytical method and numerical method through an example. So today we will see about FEA. In FEA, what is discretization process and why we do meshing and what are the different types of elements are available and what is degrees of freedom. These kinds of stuffs will be covered in our today's session. So before getting into the topic, so I am Rajit, so you are watching Simulation Tech. Okay, so let's get into the topic. What is FEA? So already you guys are already know about FEA. So in our previous session we have already seen about FEA a little bit, and FEA is a computational technique that is used to obtain a approximate solution of a boundary value problems. So it's a numerical method called finite element method. So or else we can say finite element analysis. So it's a one type of numerical method. So we have four types. So FEA, FEM and FDM, and another one is boundary element method. Okay, so what is discretization process? So in FEA, what is discretization process? Why do we carry out meshing? So I have two questions. First question is what is discretization and why do we carry out meshing? So what is before that? What is meshing? So meshing is nothing but during discretization process you will get a mesh, so that is called, these process is called meshing. So otherwise you can say, so both terms are very closely correlate with each other. So discretization is nothing but it is called as meshing. So why we need to discretize a model or why we need to carry out a mesh? So let's see an example, so which is actually seen in our previous session. So if we have a well-known shape, right, so this is a rectangle, whatever the size may be. So if I want to find the area of this particular rectangle, so I know that length and the breadth. So if I want to find the area, so what is that formula for area? So A is equal to L into B, right? So actually I have a formula for this, so that's why I can easily find the area, right? Suppose if I have a irregular shape like this, right? How to find this area of this particular region area? So already we have seen this example in our previous session. So either we can go for integration process or else I have another idea. So I can split that particular model into a definite shapes. So how should I? So either I can create a rectangle over here. So small rectangles, how much it possible, as much as possible we can create a small region over here. So and then after that you can separately calculate these area, these area, these area, and these area, these and these, and finally you have to add all the areas into one. So you will get a some area, some value, right? So some value, but it's not a accurate solution. Some of them may be some errors may be there, so 10 to 15% maybe error maybe occurs. So that is okay. So because if you need to create a new formula for this particular shape, it is a time consuming process. So while comparing, so time is money. So I don't need a proper or accurate result, so I need a approximate result. So I can use a discretization process to obtain a result. So these process to split that particular model into a definite shape, that process is called discretization process, or else you can say it's a meshing. So meshing process, that is called meshing. So this is hope you will understand what is a discretization and what is meshing. So why we'll do a meshing? So to create a to obtain an approximate solutions. So that is called discretization and meshing. So it's a basic idea of FEA to make calculations at only limited number of points and interpolate the result for an entire domain. So if you want to read the entire session, so please pause the video and read the theories, right? And next thing, right, so we have an example for that discretization and meshing. So here I have a irregular shape, so we obviously don't have any formulas for this particular model, right? So I don't have any formulas for this. So how should I actually find the area? So I need to find the area of this model. So don't go for integration process. So again, integration process is a complicated process, but in that process also you need to assume that what is that upper limit, what is the lower limits. These kinds of stuffs will be came in that particular part also, right? So to find the area, so obviously we can go for according to FEA, we can go for discretization process to discretize the model, how it actually looks like. So what I will do is, I'm going to next slide. See that same model. So we have seen this model here. So the same model is over here, but the model is discretized into a particular element shape. So obviously I don't have formula for this shape, but I have formulas for these shapes. See, I know the formula for this rectangle. To find the area of this rectangle, I know the formula. So I know this formula. So I have discretized this particular this model into a separate element. So this is called element 1 and 2 and 3 and 4. So or else I can say this is a mesh. So it's a meshed element, right? Okay, so hope you will understand what is mesh, and some other concepts are also related to this model, and these elements is called quad element. Why it is called as quad element? Because it has a 4 sides, so that's why I'm called as a quad element. And so this is the whole region, so don't bother about it. It's not a polygon, so we don't have polygon element. Only we have a certain types of elements itself only, right? So let's move on to that next slide. What is actually said in that next slide, right? So it's an example for meshing. So actually it's a 2D plane. So we have a planar surface and we measure it out as a quad element through a 2D elements. So if we have a 3D objects, so how can I actually mesh that particular model, right? So we have a question. So if we want to find the area of a particular area over a 2D or planar surface, we can use this method. So if we want to find the volume of a object, irregular object, how can I actually discretize that particular model? So a 3D model. See, here we have a 3D model. So this model is discretized by using a cube element. So if I zoom it out, so closely watch, see here, you can find that cube structure, right? So over here, so all of them are sliced into a cube, small cubes. So in this example you can clearly understand that how the entire cube is discretized into a small cubes, and the each and every cubes is separately analyzed and the results are combined to obtain a final results. So these process is called meshing or discretization, right? I hope you will understand. Let's move on to that next slide. Here we have a few questions regarding that discretization process, so or FEA. So these terms are more familiar in FEA. What is nodes, what is the elements, and what are the types of elements? So you guys are already studied about this in FEA subject while you are studying engineering, but so we will I will tell one more time. So what is nodes and what is elements? It's not a super complicated thing, so it's a very simple thing. So while we go to our previous example, so here we have seen that. So I have already said that this is element 1 and 2 and 3, right? So in element 1, so if I separate the particular element, so this is my element, right? To create an element, so whatever the element may be, so maybe it's a quad element, maybe it's a quad element or a triangular element. We need nodes to create an element. So node is a junction point of elements. So here I have a node, here I have a node, here I have a node, here I have a node. And in this triangular element, so here I have nodes, here I have nodes, and here I have nodes, right? So we don't have any triangular element over this model. So all the elements in this particular model are a quad element. So in this quad element, how many nodes are there? So here we have one node, and here we have another node, here we have one node, and here we have another node. So these nodes are help to create an element, and otherwise we can call it a node as a, so node is called as a calculation points. So why we called a node as a calculation point? So in our previous session we have seen that how actually we solve the numerical problems. In numerical problems, first of all we need to perform the discretization process. After the discretization, so the elements and nodes are created. After the node creation, a simultaneous not a simultaneous equation, before that stiffness matrix is created, so namely called K matrix, and these K matrices exactly equal to the number of nodes. So if I have 3 nodes, so it's ordered to be 3 into 3, so it's a 3 cross 3 matrix. So obviously if you have 10 nodes, so it will have an order of 10 into 10. So the more the number of nodes, more the size of the stiffness matrix is increased. So after the stiffness matrix is created, that stiffness matrix is converted into a simultaneous equation. The simultaneous equation is solved and the unknown variables is calculated. So that is the overall procedure of numerical method. So our nodes is very important, so that's why we call it as a nodes as a calculation points. So if you have a more number of nodes in your problem accuracy will more, and as well as the problem time also be increases, right? Here these node is only shared by these element only, and these node is shared by 2 elements, first one and this one. But this node is shared by 4 elements, so this one, right? And this node is shared by 2 elements itself. So nodes is a junction point of elements. It can shared by 1 element or 2 element or 3 element or 4 element, 5 to 6. So whatever it is, it can be shared by multiple numbers of elements. So that is also possible. So that is called nodes and elements. So hope you will understand what is the difference between nodes and elements. So that is a very important thing, right? Next thing, so what are the different types of elements? Okay, so while I discussing discretization process, so I need to convert that infinite boundary into a finite boundary through a particular shape, so which I have already known, which I have a formula for that particular shape. So I have a formula for circle also. So can I use circle to discretize a model? So if I have a rectangular or square surface, I need to discretize that particular structure. So can I use a circle as a discretization element? No, that is not possible, because if you discretize this model by using circles, you may face a lot of errors over here. See, a lot of unoccupied spaces are over here. So here, so you attend a more number of errors over here. So already we have so many errors in discretization. So if you use a circle as a discretized element, so it is not suitable to capture all the areas or space or volumes which are take place in our model. So we don't actually use all the shapes to discretize that particular model into an element. So we have certain set of rules. We have to follow that particular rules. So that is the main rule over in FEA, right? So let's see what are the different types of elements are available in FEA. Okay, so let's get into that next slide. Okay, so we have a various types of elements called 1D element and 2D element, and so 1D, 2D and 3D elements. So before getting into that different types of elements, you need to understand what is 1D, what is 2D and what is 3D. So for that I go to here. So tell me, so what is 1D and what is 2D and what is 3D? And so 1D have 1 dimension, 2D have 2 dimensions, 3D have 3 dimensions. So these will be familiar. So you guys are already familiar with this concept. But in FEA, So while solving a problem, we have a three different methods: 1D method, 2D method, and 3D method. And how can I actually switch over between these methods? So when I see a problem, how can I actually say, okay, I can solve this problem in 1D, or no, okay, I can solve this problem in 2D. No, these two methods are not suitable, so you can directly go for 3D. Okay, so because in real-time problem, so we have seen all the materials or whatever the component it may, so it's actually a 3D. So why should we have a 1D and 2D method? Either we can directly go for 3D now. Okay, so but we have a methods called 1D and 2D. So how can I have a clear idea regarding these methods? Let's see, what is 1D? How can I actually relate it? So is there is any real-time example which is closely related to 1D? So if I say what is the example for 1D, you guys are say, most of the people say, so best example for 1D is line. And what is the example for 2D? Say rectangle or square. And example for 3D is a cube. Cube is the best example for 3D. But these are all assumed cases. I need a real-time example. So whether you can say, okay sir, this component is called 1D, this component is called 2D. I have seen in my real-time life. So if you have any examples like that. Okay, so I will say, so how I will say the rules and regulations to switch over these methods. So how to choose 1D and 2D and 3D. Let's see about. So for that I need a coordinate system. So I can draw a coordinate system. Okay, so from here and from here and from here. So it's a coordinate system, and so obviously it is either you can say this is y. So I'll switch the color. Okay, this is y, and this is x, and this is z. I can place one pen over here. Okay, so it's a pen I place in that particular region. So its diameter is around maybe 1 centimeter. It's not diameter, it's radius. From this point it's 1 centimeter, so its length should be a 15 centimeter, right? I need to solve this problem. So whatever may be, so one end is fixed, another end is applied to a tensile force or bending load. So which method I should choose, whether a 1D method or 2D method or 3D method? So I can say this is a 1D problem. How I actually say that? See, here the length is 15 centimeter. That means in x direction it is 15 centimeter. One length is too long while comparing to other two dimensions. One of the dimension is too long while comparing to other two dimensions, right? So 15. So while in y direction it should be 1 centimeter, while in z direction it should be in 1 centimeter. So while comparing these two dimensions, one dimension is too larger. So that's why it's a 1D case. So I can solve this problem in 1D. So this is the method to select, to identify that 1D problem. So whatever the case which obeys these law, you can directly solve the particular problem in 1D. So in our later session we will see about what is the advantages of 1D, 2D and 3D. So why we have a separate analysis systems. So that will be covered in our later session, right? And so if I say I have a 2D object, so how to choose a 2D one? So, right, I have a paper over here. So in this paper, let's assume that its length is 20 centimeter, it's 25 centimeter, and x is larger and y is larger. but its thickness is very small. So let's say we can say that it should be a 0.1 mm, not centimeters, so 1 mm, right? So while comparing to other two dimension, one dimension is too small. So one dimension is too small, so that is why it's called as 2D. So what is it called as? It's called as 2D. 2D analysis. So I can solve this problem in 2D systems, right? And what about the 3D? For 3D, all the three dimensions should be compactable or comparable. So either it should not be too small, nor it should not be too long. All the dimensions should be in an equal space. So I have a cube over here. So to solve this problem, so whatever may be, so some forces may be applied on the top of the part, bottom may be fixed, whatever the condition may be. So I can directly go to a 3D. So why? The reason is because it's a x dimension, right? So these dimensions is x dimension, and these dimension is z dimension, and these, what is this? This is y dimension. So all the dimensions, let's say let's assume that this side is 10 and this is 15 and this is 10. So all of them are comparable with each other. So either one is not very small or very large. So that's why we can say this problem is a 3D problem. Okay, so we can directly go and solve this problem in 3D itself. So this is the methodology to choose whether I should solve this problem in 1D or 2D or 3D. So hope you will understand this concept, and if you have any doubts regarding this, you can comment in the comment section, right? So based upon the method, so if you want to solve the problem in 1D, so you can choose 1D elements, or if you want to solve the problem in 2D, you can choose 2D elements, or you can choose a 3D elements. So if you want to solve the problem in 3D, right? So what are the elements are available in 1D? So in 1D itself we have only one element, so that is called a line element. In line element we have one element and two nodes, so one node and two nodes, namely called n1, n2. So in the previous session we have solved one problem in numerical method, so that is also a one-dimensional problem. So we have a line element, two line elements in that particular problem. So n3, so this is element number 1 and this is element number 2. Okay, right? So this is a first order element. So what is the difference between the first order element and second order element? So usually we have only two nodes in a one single element. Okay, but for some cases or some flexibility or more accuracy, we need an additional calculation point. So an additional node is created in between the two nodes. So here, see, you can notice that an additional node is created over here. So here also an additional node is created over there. So that is called second order element. So these elements are more flexible and having more accuracy, but having more time to solve the problem. So it usually takes more time to solve a problem. So due to that size of the stiffness matrix, right? So if you want to solve that 1D problem, so for example spring, dampers, beams, truss problems, so these problems are usually using one-dimensional elements. So what about the 2D elements? So if you want to analyze a cardboard or paper or sheet elements, sheet metals, whatever it is, you can use shell elements or 2D elements. So usually you have two different types of elements. One is quad element. So this is quad, so it has a 4 sides, right? Quad. And another one is triad, so it's a triangular element. And in second order element itself, it has a quad element and a triad element. So one more configuration is also available, so that is called R triad configuration. So we don't usually use this configuration, but we have this configuration also. So this is called or tria. So that is means a right angle triangle. So or tria. And so that is all about 2D. So in 2D itself we have only two elements, element shapes, right? Quad element and triangular element, and or tria itself, right? It's a one type of another type of triangular element. And what about 3D elements? In 3D elements, basically we have in most of the cases we use tetrahedral. So that is tet element. So how actually a TED is created. So these elements are actually created from this 2D elements. How it actually creates. Let's see. So if I have a triangular element in that perpendicular direction. So in that perpendicular direction I have one single node. So from this node I can join this and terminate of that triangular element. So I will get a tetrahedral. So if you need a more accuracy, you can shift to that second order element. So you can have an additional nodes over here. So these points also covered with this nodal points, right? And what about the hexahedral? So I have a quad element. So I have another quad element over here. So if I join these two, I have a brick element or hexahedral element. So it's a high quality element. So usually it is very difficult to create this quad element in a complicated structure. So unless or until it's a very simple model, we can easily create a hex element. But if it is there is a lot of curved surface or irregular surfaces, it's very difficult to create a hex mesh over there. So usually we use tetrahedral, right? So but it has a more accuracy. So it has a first order element and second order elements itself also. So we have one more configuration over here also. So that is called a prism. So similarly, how we actually create a hex elements by using two quad elements or extruding a quad element. So I have a one triangular element and another triangular element. I can join these endpoints. This is called a prism element. Prism. So it has a 6 nodes in first order and having 10 nodes in second order elements. So this is also another configuration, right? So let's move on to our next slide. So that is okay. So again it's a 3D elements. So it's having a more clear example to how it's flexible, difference between that linear and quadratic. So linear means first order element, quadratic means second order elements. And so first is tetrahedral. So we have 4 nodes in normal tetrahedral and 10 nodes in second order tetrahedron. And in prism element, so we have 6 nodes in normal prism and we have 15 nodes in prism, that means second order prism. And in a hexahedral, in first order we have 8 nodes, in second order we have 20 nodes, having more flexibility. So see, so if you want to capture the entire area, so you can use the second order elements, or otherwise you can go for first order elements. So that is recommended, right? So we have one more configuration, that is called prism. How it actually created. So some softwares will support that prism element. So Ansys will support that prism. And how it actually means is I have a quad element. So in that perpendicular direction I have a node. So what I will do is I just join this all the endpoints by using this. It's look like a pyramid. So that's why it's called as a pyramid element. So in pyramid element itself, we have a first order element and second order element also, right? So these are all the different types of element shapes available, depend upon the types of elements: 1D elements, 2D elements and 3D elements. In 1D only we have line element, in 2D we have a triangular element and quad element. In 3D itself we have a tet element and a hex element, pyramid element, prism. In Ansys itself we can say that it has a weed element. So weed means a prism element, okay? So these are all the different types to discretize a particular model as an elements. Hope you will understand this concept, and let's get into the next slide. Right, so finally we are here. What is degrees of freedom? Degrees of freedom. So if you learn a design software, you probably heard about what is degrees of freedom and what is constraints. Okay, so let's see an example. For that I need a coordinate system. Okay, so let us assume this is a coordinate system, and you guys are already know that this is x and this is y and this is z. So DOF, a DOF means, so we have totally 6 DOFs, so 6 degrees of freedom. So 3 is translation, so trans, and 3 is rotation. So translation in along x, y, z. So translation along x and y and z. So that is it. First 3, and second 3 rotation along x, y. So how can I say what is that rotation along x and y? So rotated about x, rotated about y, rotated about z. If I place a component in that particular coordinate system, so that ability to rotate in about that x-axis, about y-axis, about z-axis, or ability to move towards x, towards z, and towards the z direction. So that is called translation and rotation. So if we log that all the 6 degrees of freedom, how it actually acts is, it acts as a fixed support. So that means there is no motion over here. So depend upon the problem statement, we can change the 6 degrees of freedom according to our wish. So that is all about degrees of freedom. So that is the final concept of this particular session. Hope you will like the entire session. So if you like the video, please give me a thumbs up and subscribe to our channel. So we will see in our next session.